Alrighty, I think we are live. Episode 3, episode 4, indexed 3. Welcome to How Things Work. Today we'll be talking about scaling broadcast with Raptor Codes with some awesome guests here. Before we get started, want to share a quick disclaimer. This podcast is for informational purposes only. Nothing said here should be interpreted as an offer to buy or sell securities, financial advice, legal advice, or as an opinion of the employers at which anyone works. Lastly, our guests and I may hold positions in the companies or projects discussed. Now, with that out of the way, welcome to How Things Work. I'm Patrick, the host here. I'm founder of Commonware and previously was head of engineering at Babel Labs. Today, we have two guests on. The first is Kushal. You want to introduce yourself, Kushal?
Sure. I'm a researcher at Category Labs. I recently finished my PhD at Cornell Tech, working with Ari Jules. And the kind of things that I usually research, although I do research across a broad spectrum, I usually try to look at crypto economics, systems, and overall protocol from a higher point of view. And of late, I've also been involved in some applied cryptography work as well.
Very cool. Yeah, Kushal and I got to know each other at at an IC3 retreat, I think a few years ago, and we were sharing fondue in like a cabin or something like that. So it's good to see you. Good to see you again.
Yeah, in the chalet.
Yeah, yeah. And then we also have Babak here. You want to introduce yourself?
Yep, sure. I'm a senior cryptographer in Category Lab. The focus of my work in Category mostly is related to cryptography, but like authentication and cryptography is also involved in like block propagation. That's how I got into the block propagation stuff. Thanks for having me here, Patrick.
Yeah, excited to chat. Yeah, the joke I tell with people now is everyone's like, why are there so many cryptographers around here? And it's like, well, everywhere you look for optimization, there's like a cryptography sized hole. So I'm talking to more cryptographers than ever. So it's always a fun conversation.
Well, there's a reason cryptocurrencies are called cryptocurrencies.
Yeah.
Fair enough. Yeah. See, you know the podcast thing. You know how to get the zingers in like that. So very excited to have this. So backstory here is, I've been talking to a lot of different teams and engineers around like just optimizing the performance of blockchains and consensus systems. And what always comes up is definitely this broadcast question, which is like, okay, how do we get data around a network to all the participants? And more than ever, there's been an explosion of different ideas of how to do this, whether it's pre-consensus dissemination, like doing some, all sorts of different encoding schemes, working with different topologies of networks, layers of communication and everything. And so when I saw your guys' blog post, so Category Labs, for those that don't know, is working on the Monad reference client and doing a lot of work in that ecosystem. Saw this blog post about the work you guys were doing with something called Raptor Codes. And not only did it sound super cool, I was like, I would love to have them on to kind of talk about the problem that they're looking to solve and get really to the bottom of why encoding schemes and all this very cryptographic heavy broadcast is becoming such a popular idea in the space. So I think before we get into all of that, I think it makes sense to first set the table a bit and talk about what is broadcast, what problems it's solving, and what have people kind of historically done over this trajectory of let's call it like broadcast evolution, which starts off just sending bytes over the internet and then obviously has evolved quite a bit from there. So first, let's maybe just start off framing the issue. What is this broadcast problem and how does it apply to the work you guys are doing?
Sure. So we can take a step back and we can see, start from what we are building. So we're building blockchains, which is a series of decisions about, users' transactions. And you can imagine that users' transactions do carry data around how much money they want to transfer, what kind of data they want to call their smart contracts with, and so on. So once a user sends the transaction to this distributed group of nodes that are running the blockchain, you want that data to be replicated across all those nodes. And so the question is, how do you make this data available to the distributed network? And typically in a leader-based consensus protocol, there's a leader who collects all these transactions in a block. and then disseminates this transaction to the entire network, which is what we call broadcast. Now, there are different features of broadcast that I think we can get into. There's best effort broadcast, where you just try to send messages and hope that they reach their destination. Or there's reliable broadcast, where you do make sure that as long as the leader is honest and under some good network conditions, every honest participant would receive the message. And then there are other flavors of it, which also enforce ordering constraints on how these messages are delivered, so that you can have a consistent view of the evolution of the world. So at a very high level, broadcast is just making data available, typically from in a leader-based protocol, typically from the leader to all the nodes in that system.
And I think maybe to ground this a little bit too is like, obviously a lot of people are familiar with Bitcoin and Ethereum. What do they do, right, to solve this problem?
Right. I mean, Bitcoin, with the context that it was originally, developed in more than a decade ago, and roughly the case for Ethereum now as well. The approach is quite simple, and it works at the time horizon that Bitcoin and Ethereum are targeting, which is in Ethereum, you want to get the block in 12 seconds to the entire geographically distributed network, and in Bitcoin you have more time than that, typically on the order of minutes, around 10 minutes or so. And so you have a lot of time in just sending the block to the network. And the strategies that they deploy are typically called gossip-based strategies, where you basically flood the network like an epidemic. It starts from the leader as the source, and then you flood the network with blocks. And you have enough time to basically make sure that after a lot of flooding and everybody gossiping things to everybody else, after few seconds or minutes, the data would most likely be available to every node. And so this is how Bitcoin, Ethereum, make sure that in the peer-to-peer network, the data is mostly available to everybody.
Yeah, I've always thought about this as two comments. One is like, I feel like as you get deeper into consensus and some of this like low level blockchain architecture, all of a sudden like things that people just kind of took for granted, it's like no, we have to rebuild it. And so like motivating a lot of that always becomes useful. Otherwise people just feel like we're just reinventing the wheel for no reason. So my framing around some of this is like, because Bitcoin and Ethereum were originally conceived as proof of work chains where you had no idea who was participating at any point in time, it was kind of difficult to do anything more complicated than just a best effort thing. Similar to like in the case of like torrent networks and some of the other like early, popular uses of P2P. You don't know who's going to be online when, and you don't know who's going to be building where. And so the idea that you can somehow like map a lot of that is exactly why I think early P2P systems that didn't just do this like best effort approach often ended up failing. Now there's a lot of pros and cons there. You called one out for sure, which is like, it can be real slow to get something from one side of the network to the other. And there can be a ton of wasted bandwidth as you like resend the same thing over and over again, because you don't have any idea what like the logical hierarchy of like the broadcast thus far has been. But yeah, and I think the big thing that opened the door to me where things got a lot more interesting was in this like proof of stake context, where all of a sudden now we have this notion of who's around. So I don't know if you want to take it from there as like, well, if we know this, what can we do differently, I guess, than just sending things randomly?
Right. Yeah, that's actually a good point, that in the permissionless setting, you don't know how to organize the network, and you don't even know who are the nodes in the network, right? So it becomes difficult to design a broadcast strategy. But in proof of stake, it's a permission protocol, and so you know who the set of nodes is, and very often you know the leaders also in advance. And so then you can design a clean strategy. For example, organize them in a tree-like fashion, organizing them where the root of the tree is the leader, and then the nodes in the tree are rest of the nodes, and then you can have multiple levels in the tree. But then it becomes possible to have these kind of structured approaches where you can organize the tree beforehand. There's some randomness involved in some cases, but largely you can figure out a clean, structured way of disseminating this data rather than just a local gossip-based protocol. So that's one big advantage of having a permissioned protocol.
Yeah, I think there's just so much you can do if you know the full set of participants at some point in time, I think, to like really optimize this stuff. I think where this conversation gets interesting, and because some people would say like, well, why don't I just send the data to everybody? Like, why do I need all this fancy stuff? And like, why do we have a cryptographer here? And so I think that the question is, well, why don't we? What's the problem? Like, why does this not just work to send? Like, okay, well, I know everyone that's a participant. Instead of just sending the data randomly, why don't I just do the same kind of thing, but just send it to everybody? What happens?
Yeah, I'll let the cryptographer take that one.
The thing is, like, I mean, one good thing about not knowing the nodes is that it makes it harder for the adversary to corrupt the nodes. So if you don't know the nodes involved, unlike like if you know all the nodes beforehand, so you know exactly who to target. That's one thing. So I didn't understand your question about how the cryptography involved in the chunks that in the data that we are sending. So I mean the part that the cryptography is involved is for the authentication of the data that we are sending. So sometimes the goal is to use the bandwidth of all the nodes. So I mean the most naive approach is to just the leader sends all the data that he wants to send to all the nodes one by one. But that requires that takes a lot of bandwidth from the leader. So the whole idea of to design a system like a Raptor Codes or any other like system like just hop like the gossip approach, all of them, the idea is to use the bandwidth of those intermediate nodes. So to not like only rely on the bandwidth of the leader. Now when we are relying on the bandwidth of an intermediate node, we need to make sure that node is honest and kind of like not kind of just rebroadcasting some wrong data by himself. So that's where cryptography comes in. And we try to make sure that we can get into the details how we do that later. But for now, we need to design something to make sure that the data that those intermediate nodes are sending to each other are kind of like authenticated, are just coming from the original leader. If not, the receiver can easily like detect that and throw them out, or potentially even just block the sender for future to avoid like the future problems.
Yeah, I think you brought up a good point there too, which is something to discuss probably later as well, as like this DOS that opens if you start to like flash the consensus identity of the participants on the networking layer, because everything's DOS resistant to a point against like a big enough attack. So like as soon as if you know the IP address where someone is, like it's just a matter of scale in terms of until you bring them offline. Whereas the idea with a lot of these original P2P networks, which made them so reliable and robust, was that as long as you weren't getting Eclipse attacked, which maybe we can talk about also later, but you were tough to find, tough to shut down, tough to like kind of mess with, and unless you like took over the whole network, which just because the way peering worked was not always really possible. But yeah, to get to the question at hand, like
Patrick is frozen for me.
Oh, there we go. I got freaked out for a second. Sorry. Can you hear me good?
Yeah.
I think I think you guys have a quote, or at least in the blog you guys wrote, this Raptor Codes designing a messaging layer, where you talk about like for an instance with 1,000 validators and a block size of 2 megabytes. That's about 2 gigabytes of data that go out from the leader at just like one point in time. Now, sure, you can design like all sorts of, or like acquire all sorts of hardware that makes that a little bit easier to go out. But at the same time, you kind of have to look at this reality of saying, well, the other validators, 999 of them, are not really doing anything to help distribute that data through the rest of the network. And it may actually be faster to distribute that load rather than having like a single party try and do this massive multicast out. But yeah, as you brought up, you start to trust other people to help you kind of disseminate this thing. It opens up a whole nother can of worms. And so that authentication topic and how like this cryptographic abilities you can add to the protocol to make it more robust can help in a big way. So let's dig into that. I mean, like I think the idea of we have this we're starting from this naive point, which is to say, great, like I'm trying to build a really fast blockchain. I just have a leader that's going to send everything out. Maybe with 50 nodes, this totally works. But now you scale like 1,000, and all of a sudden it's like you're trying to push massive amounts of data out very spiky from every node. So how should we think about this? Like what have other people done to try and get around this issue? I know a lot of people talk about like Turbine and Solana a few years ago was kind of the one that really started to popularize this idea. Maybe you want to summarize kind of some of that approach and what it entails. Yeah.
Yeah, I think if you also look at the way we have structured the blog post, it basically talks about three kinds of things that you want to solve. So one is the broadcast strategy that we have been talking about, which is how do you organize the network? In some sense, this is the topology of the network. So is it like a single leader to everybody else, or is it a local peering strategy, or is it you organize them into multi-level trees, and then which nodes go where in that tree? So this is part of the broadcast strategy or the network topology. Then the second one is what kind of network connections these nodes are using to talk to each other. Is it TCP? Is it UDP? Because that determines how much reliability you have in terms of your data delivery. And the third one is the what data you are sending. And so it could be either the full blocks, the raw data, or it could be a smart encoding of those, which is what, for example, you brought up Solana's Turbine system. So you can encode the data a little bit more smartly than what, for example, would be a naive approach where you just send the data, serialize the raw data. And so having more smarter encoding schemes helps you tolerate some of the faults during the data dissemination. So either faults of omission, where some data is just plainly missing because of network conditions or faulty nodes, or some corruption on the way. For example, if you're not using TCP, then you don't get you don't get integrity from, for example, from UDP. And so this encoding system and authentication that Babak was talking about also helps you get over those kind of errors. So there are kind of all these approaches that we've seen before explore different designs along these three aspects. So if I had to kind of my understanding for example for Ethereum is that the full blocks are being broadcasted. So that's the data part of it. The network topology part of it is the peering part of it, which is everybody just connects to their local peers and only manage it, and you only have a view of your local surroundings, not a global structure. And I think for delivery, you can use either UDP or TCP. That should be fine. But that's one way of doing it. Then the other way of doing it is what Solana's Turbine has been doing, which is you also encode the data into small, what they call shreds, where you divide up the data into small chunks. And then as long as you receive sufficient number of chunks, you can reconstruct the original data. So they also add encoding layer on top. And they have a structured, in Solana, there's a structured way of disseminating the data. There's some randomness involved in which nodes go where, but there's a complicated way of having neighborhoods for nodes, and then the leader sending the data along the tree. And then there are, obviously there are trade-offs in every approach. When you go from one to the other one, we can discuss the trade-offs, but this is how largely things have evolved from Bitcoin to Ethereum to Solana.
Yeah, so I think the summary, just to kind of wrap that up, right, is to say, right, in Bitcoin and Ethereum, you kind of just randomly connect to random people, maybe seeded from like some original boot nodes that have a list of peers you should start to connect to. You hear about other people, you randomly connect. When you have data to share, you just kind of shoot it out to those people you're connected to, and then they kind of shoot it out to people they're connected to. And eventually, somehow, everyone kind of finds out within some amount of time. The next step is to say, well, what if we instead are very specific about how we break this thing apart and provide some cool properties with it that we can just push pieces of it to certain people, and then they'll push it to very specific sets of other people. And then under certain assumptions, the recipients of that data will be able to recover the actual full data, although like people along the path may have been sending them pieces all the way along. Is there anything you'd add to that, or that kind of sounds like the right bend?
Yeah, the one thing to add is like, so the leader, we don't. So the reason that we are doing all of this is to not rely only on the bandwidth of the leader. So and the bandwidth of all those nodes, but we also need to make sure that we are not relying too much on the bandwidth, and we are relying exactly the amount we should on the intermediate nodes. If we rely too much on them, because we don't know if they are reliable, if they are honest nodes, if they are not honest nodes. So of course, if we assume all the nodes are honest and they have the same bandwidth capacity, the best approach is to just rely on them equally. Just let's rely on each node, including the leader, just equally. But the point is, like, some nodes are less reliable. So in proof of stake networks, the way that we understand that how much this node is reliable is based on their stake value. We generate some sort of, like, we kind of like allocate some weighted number to each of those nodes, and that's how we understand how reliable are they. So Solana, they used to actually they have changed their approach about a week ago. So they have generated a new, like, broadcasting approach, and they call it Roder. So before that, they were using Turbine. So in Turbine, yes, they have like two hops and like three layer of like broadcasting. So the more hops that you have, the more like network latency you will see. And also they used to have some sort of like randomized kind of like selecting those intermediate nodes based on, again, weighted stake value, but still it was randomized. And now because you don't know the randomization, like, you may be unlucky in those randomization, maybe there is a chance or probability that when you are signing those chunks, they all go to some sort of like unreliable node. So now they are also going toward more like deterministic approaches.
Yeah, and I think to be fair, if I may just add one thing about the literature. So we also have to talk about typically how when we write papers and we kind of read up the literature, how these things are described. So it's a bit strange to me, at least, that when we kind of read descriptions of consensus protocols and consensus papers, this thing often gets overlooked, and papers just mention that, okay, if you have to design your system, the leader just broadcasts, and that's considered one round, and this round is considered, like, at par with the next round where you're just transmitting small votes to everybody. So everybody's either talking to one leader, as in hot stuff, or everybody's talking to everybody else, as in like PBFT, but those are transmitting small messages. So that's one round. But the round before that, where you're making the proposal, that's also considered one round. And typically you say the latency of my protocol, consensus protocol, is just 3 rounds or 4 rounds or 5 rounds. But there's a big difference between what you're doing in these rounds. So the first round, you just say the proposal is sent to everybody. Sure, but as you mentioned, and as we kind of outlined in the blog post initially, that's a lot of data to be disseminating. And so if you are a little bit smarter about organizing it, as we are discussing, then Babak was mentioning you can have more latency. And so then you get more rounds hidden within a round. And so it's a bit strange that in theory and practice of consensus protocols, this is one big gap that I see, where papers just define abstractly how data will disseminate and then still are able to talk about latency. But when we go to practice, we have to add in additional hops, which do contribute to more latency of these protocols. So so that's one thing that I wanted to mention, which is also, like, important part of the puzzle.
How are you going to get into conferences if you have to talk about all this extra latency?
Yeah, it gets very complicated very fast, right? And not just with respect to the system side of it, but if you also talk about incentives, right? In papers or in literature, we typically say, okay, if the block is not disseminated by the leader, we'll just penalize the leader because it's the leader's fault. But when we implement in practice, we are leveraging everybody else. And so now we want to say that, okay, if some nodes are actually faulty within this tree, then maybe it's not the fault of the leader, maybe it's the fault of everybody else. And so it becomes complicated to reason about reliability of these systems, even from an economic point of view, not just a systems point of view. And that's why I think, because of many of these complications, we just abstract it out in literature and struggle with these problems when we go to implement these theoretical constructs in practice. And particularly one subtle point here is that it's more challenging because at the network layer you don't have consensus. This is a building block for consensus, so there's a recursion layer. So if you don't have consensus at the network layer, how do you agree on whose fault it is? For example, so if I want to design an incentive scheme where I say, okay, I'm going from leader to all versus a tree-based broadcast, and then I want to design my incentive structure and other things around it, but I don't have agreement on who's faulty and who's honestly behaving, because you don't have consensus yet. That's what you're building towards. So these are all messy details when we build practical systems.
Yeah, the gap sometimes between what's written and what's coded can be quite immense, which I think to some degree is I think there are quite a bit of mechanisms hidden in the space that are maybe less robust and less considered than people realize, because there are some gaps where it's you got to launch it, so you got to do something, and I think sometimes those are not quite as rigorously considered. Maybe I think another one, kind of unrelated, but is this there's a lot less focus on reconfiguration in these consensus papers as well, in terms of actually practically implementing a blockchain, right? Especially over a permissioned construction, because it's kind of all right, well, you just wait for some number of blocks to pass and you consider whatever happened to be finalized, and then you can reconfigure based on that. Or very hand wavy. Fortunately, I've heard there's some good work coming down the pipe there that I'm pretty excited about. But that to me is another example where it's kind of yeah, we're just going to talk about this consensus as it's currently instantiated, and then yeah, if you want to actually add people and remove people, that's kind of out of the scope of this work. So yeah, it's a whole different thing. But yeah, I totally agree that it's an interesting point with the way consensus papers are written, where the proposal is just considered oh yeah, just send it out, easy, and then yeah, it's just happens. So I think it's the same thing with leader relay driven protocols as well, where you kind of assume that you're just going to be able to collect all the messages in kind of pull them together and send it out. Every time you add a step in this process, or some set of people responsible for something, determining fault becomes, there's another layer of complexity to doing that. So I guess, how do you guys think about that with introducing these much more complicated, networking procedures here, right? Because it's kind of this all or nothing thing, where it's if most of if the supermajority is honest, it should just work, I guess, and that we shouldn't really maybe reward everybody for that happening. Or is it something where you think it's a good idea to try and assign, or attribute work to people that are actually participating in this thing, maybe based on how you decide to split up the pieces of the broadcast? I think that's a interesting route to go down as you think about adding complexity to every layer to drive better performance.
Yeah, it is a very challenging problem, right? For the simple reason that it's very difficult at the network layer to assign faults. We have some interesting optimizations actually to this paper that another paper that we published recently called Monad BFT. We have some interesting kind of optimizations in the pipeline where, in some cases where it's obvious, you can figure out whether the previous leader, for example, you were mentioning, leader is aggregating the votes and then sending it to everybody else, and so on. There are cases, many of the common cases where you can actually figure out whether it was the previous leader who failed to disseminate their block, or whether it's the next leader who failed to collect votes on that block, and because of that, the previous block was abandoned.
Interesting.
But still challenging because there are always cases. Precisely, if we agreed, then we would have solved consensus. But there are many common cases where you can assign blame. There are also some recently very interesting work that has come out around accountability for these liveness faults. Typically, when we think about accountability, we always, like in Ethereum's context, we always think about slashing, right, equivocation, and so on. But accountability for these omission faults is also very, very interesting.
That was Joachim's most recent work, if I'm not mistaken, right, from A16Z research. Yeah, I talked to him about that. Super interesting. Yeah. Yeah, so I think we've danced around kind of like more of the specifics here of what you guys have been working on, and I think this establishes a pretty good basis, which is to say, hey, you like want to scale up broadcast here, like you can't rely just on the leader. So what do? You try to slice it up somehow. So let's go into that. So like there's these things called Raptor Codes, I guess. There's these things called like coding schemes that allow you to do this in some way that's more intelligent than just pushing out the whole thing to everybody. What is that?
Yeah. So I would say like there is no like good or bad encoding system. So we need to choose the encoding system based on our needs. So and what are those needs? So it depends on the block size. So if we are dealing with a small block size, so maybe RaptorCast is as good as like Reed-Solomon like solutions. So, and also it depends on like how noisy the network is. If the network is like super noisy and all the like chunks or those slices of data are being lost, maybe RLNC is better. So if we have like 50% of loss. So that's why, I mean, it depends on the data that it depends on the requirements and the network states that we need to choose our encoding systems based on. So what good about Raptor Codes is a very fast encoding and decoding system with even high number of chunks. So for Reed-Solomon, if you have anything above, like by chunk, I mean like when we divide the data into like some small chunks, like even if you have like 3,000 chunks, still you can manage a very fast encoding and decoding in the range of like 3 milliseconds encoding and 10 milliseconds decoding. So that's why actually we have chosen Raptor Codes. So that's the good thing about Raptor Codes. Unlike like Reed-Solomon, for Reed-Solomon, when you go to anything above like thousands chunks, then that would become super slow because that's the polynomial interpolation for so many points, and that the decoding becomes super slow. That's one thing. And in general, like RLNC approaches, the decoding and encoding is very slow because it has some matrix inverse involved. And for very big like data, for 3,000 like chunks, the matrix inverse is almost like impossible. In terms of our block time, like the cat monad block time is around like 500 milliseconds. So that's why we have decided on Raptor Codes. But in general, like Raptor Codes, the idea is to just kind of like XOR different like data to each other and like the different chunks to each other, and try to kind of like store the pattern and the equation and try to kind of like decode them on the other side. So you may ask, so if you just generate some equations with like XORing different chunks to each other, on the other side, you may also need to kind of like solve those equations, and solving like 3,000 linear equations is expensive. It's the same as RLNC. So that's where the kind of like the peeling and LT peeling comes in. So this is how it works. So imagine.
So before we get into it, because I think you said a lot of stuff there, I just want to make sure we're on the same page on it. So you mentioned that Reed-Solomon is much slower than some of the like stuff with Raptor Codes. Are you trading off anything for that? Like I know you mentioned it's all XOR based versus like these commitment schemes. I would assume that the commitment stuff can give you something maybe that the Raptor Codes cannot. Is that true, or is it just Raptor Codes are just a smarter way to deal with the same problem?
No. Reed-Solomon gives something. So the good thing about Reed-Solomon is that kind of like no matter what chunks you receive, they are all equal to each other. They all could be interchangeably used. So imagine if you need 16 chunks to be able to decode, no matter what chunks, they are all equal. They are some sort of points on the polynomial. And then no matter like what points you get, as long as there is no like linear dependency between those points, unlike the Raptor codes. There are some sort of like linear dependency between those equations, that there are chances, with some redundancy you can avoid that, but still there are chances that you may receive like enough chunks in terms of like numbers, but there are some linear dependency between them and you are not able to decode. So that's the downside of the Raptor codes.
Got it. That's really, I think, important context to provide there too, to kind of think about this.
Thanks for bringing it.
Yeah. And then the other thing really quickly before you get into describing exactly how this works, and sorry to interrupt you, is you mentioned early on, Kushal, like this choice between UDP, TCP, and Quick. A lot of what you guys are doing is basically built over UDP, and instead of having like all of this retransmission and integrity provided by like the transport layer, you are using these like this actual like broadcast scheme to help you determine that things are actually like that they haven't been tampered with and that they came from the right place. Is that true, or am I misinterpreting that as well?
No, I think this is related as well. So it's not like a completely orthogonal dimension. It's related because if you were transmitting through TCP, then you have much better reliable delivery of your packets, and then you have to tolerate much smaller faults of omission, and you can probably reduce the redundancy of this scheme. And as Babak was mentioning, you could choose your coding scheme according to very low tolerance for missing data. But of course, there's trade-off where TCP, we know that it's a connection-based thing, and you have to establish handshakes. You have to kind of do a bunch of things to make sure that you have this reliable delivery. And compare that to UDP, where it's a best effort system. So you now have to design your system so that you tolerate both a higher chance of failure of delivery and some chance of also corruption of the data. And so you have to build in authentication for handling corruption, and you have to increase your redundancy than you would have otherwise with TCP.
So it's kind of like baked into the same thing. Instead of just like relying on TCP to give you some of these properties, you instead I don't want to use the word amortize because it may be a gross overstatement, but like the idea that you almost like say TCP, don't do this for me, just give me the raw bytes. I'm going to use like a more integrated scheme to handle the broadcast that will take care of some of the stuff that TCP would otherwise do for me. I think is maybe
like if you look at TCP, you are trying to deliver every packet reliably, and there's a good reason we use UDP, for example, for streaming, where we don't care if small bits of video or audio are kind of dropped, as long as we have sufficient number of them, as long as it doesn't disrupt the viewing experience. If some small packets are dropped, that's fine. And similarly, what we are saying with encoding systems here is that if some small bits are dropped or a little bit changed, we will design at another layer tolerance for for recovering from those errors, so that our viewing experience, or in other words, so that our kind of reconstruction of the block doesn't get affected.
That's a good pun with consensus views, but yeah. All right. So to continue, what are Raptor codes and how are they working?
Yeah, before getting into that, I also want to add one thing to the UDP part. So we don't have that checksum and data integrity that we get from the TCP, but we need to kind of like make up for that in UDP. So in order to do that, what we are doing, so still anyway, both for TCP and UDP, we need kind of like authentication of the chunk that we receive, the packet that we receive. So, and that authentication automatically gives us that checksum. So, because the signature won't match if some corruption happens on the data. So we can kind of like, it's kind of repetitive if that checksum that we have in TCP, because that authentication kind of like gives us that feature automatically. So I also want to just briefly talk about the authentication approach that we are using. So the most naive approach to do the authentication is to let the leader sign each of those chunks. So then if an intermediate node just try to kind of like change the data or to send any wrong data, then they don't have the sign of the leader on that data. So it could be easily detected by the receiver side. But imagine again, if we have 3,000 chunks of data, 3,000 signature, so that's exponential just on the group element. So that could become really expensive on the range of maybe 30 milliseconds, something like that. We want to kind of like find a way to avoid that. So the idea that category is using is to kind of like generate a Merkle proof and just signs the root of the Merkle proof for a group of the data. So so one way again to do that is to just imagine for all of those chunks that we have. I'm just explaining in a spectrum of the solution. One end of the spectrum is to just sign, to ask the leader to sign all the chunks. The other end of this spectrum is to just generate one Merkle proof of the hash of all the data, all the chunks that we have, and ask the leader to sign the the root of that Merkle proof. So again, there is a downside with this end of the spectrum, and the downside is like now, if you have 3,000 chunks, the proof size is going to be log of 3,000 in the range of 12 extra hashes for each of those chunks. So that hurts the bandwidth. That hurts that makes each of the chunk to become like 300 kilobytes only for the proof, for the authentication. So we also want to avoid that. That's why we find kind of like somewhere in between. So of this spectrum to optimize this approach. So select, let's say, 64 chunks and ask the leader to sign the root of those 64 chunks. So I also wanted to mention that for the authentication purposes.
It all becomes like a forcing function based on like, I think like what the MTU size is, right? Of like a lot of these UDP packets, which is like, you got to make sure you fit in this little box. And it's like, all right, we got this little box to fit in. How do we best use the space in this little box, right? The other point you mentioned too on the signature verification side, as people should probably know, verifying a signature much more expensive than verifying a checksum. And so there's something to consider around that point too, which I think you guys have also spent a little time thinking about with this kind of chunking.
Exactly.
Go ahead.
Regarding the Raptor codes, so the main idea is to just like just imagine we have kind of like a big block. We just create n chunks, let's say 3,000 chunks of the data. This is the base of the Raptor codes. It's called LT codes. So, and then I will explain how to go from LT codes to Raptor codes. So what we do is we divide the data into n chunks of data, and then we just generate a couple of like linear equations out of these kind of chunks. You can combine some of them, like the first chunk, second chunk, and sometimes you can even have like just send the chunk directly, because that's also a linear equation with degree 1. That's what we mean by saying degree. Like degree 3 equation has 3 chunks XOR to each other. So, and then we can generate as many as equations that we want. Not infinite, but definitely like big enough to just generate enough chunks to enough equations to let the other side to decode. So, but the design of the degree is the kind of like the beauty of LT codes. So if you design the degree of those equations in a very specific way, you are kind of like enabling the other side to solve those equations without any like matrix inverse involved. So here is how it works. So imagine like there are so many degree 1. By degree 1, I mean like exactly the chunk value. Like you are not you haven't XORed that chunk with any other chunk. So if you receive them, you can immediately say that I have the chunk value, right? So because they are like degree 1, if you receive like, for example, chunk 3, you have the value for chunk 3. So now what you are going to do is you go to degree 2 chunks. So, and now you XOR the chunk that you have already released with the degree 2 chunks. So imagine you have received chunk number 1, and now later you receive the XOR of chunk 1 and chunk 2. So you don't need to solve that. All you need to do is to XOR chunk 1 with the equation that you have received, which is chunk 1 XOR chunk 2. If you XOR them, you will automatically receive chunk number 2. So, and then now this becomes degree 1. So kind of like you can solve them. You can just find all those chunks value without any linear equation solving with some sort of like matrix inversion. But the downside of the LT codes is they may get stuck. You may at some point there is no degree 1, there is no degree 2, and you have just some sort of like long linear equations containing so many different chunks. So what should you do? The LT says, all right, that means the decoder fails. But Raptor Codes says, no, at that point, we just do some sort of like inverse metrics on the remaining the data, on those equations that we haven't like solved yet. We haven't like found the result. So that's how the Raptor Codes improves on top of the LT code.
So you basically do this really fast XORing when you can, and then when you get stuck, you then apply this more complicated scheme to try and recover the remaining pieces. All right, dumb question time. Yeah,
sorry,
so like
for people who would want to like search for some of these things, the fast method is called peeling, where you are essentially peeling the chunks one by one. So you're peeling degree 1, and then you get some source chunks, and then you take that collection, you peel the second degree with the help of this one, and then you get more and more chunks. And then when you kind of are not able to do that anymore, then you resort to, as Babak was saying, you resort to matrix inverse, like Gaussian elimination, like the kind of things that we learn in middle school for solving linear equations.
Well, some people learned that in middle school, I guess, but Gaussian elimination wasn't in my middle school. So you mentioned that like sometimes you get stuck eventually and you need to fall back here. Does the prover have, I guess, like the one that generates these like chunks, have any control over like
it depends on the degree distribution. It depends on the degree distribution, and also that was one of the things that I mentioned about the difference of Reed-Solomon and LT codes, like Raptor.
So based on what you receive, you may be stuck, basically.
Yeah, and so it's not terrible, like because the remaining of the chunks, so it's still probably like it's going to be very small matrix inverse. We make sure that like at least 50% of the chunks are degree 1 or degree 2. That's how the degree is designed.
Got it. And so the idea is then, okay, so the leader produces all these chunks. And how fast is that typically for like a block of some of these sizes? I don't know if you guys have benchmarks on that, because I think people hear sometimes all these like fancy math things and like, well, that probably takes some time on its own. So
yeah, it's very fast. It's for 2 megabytes of like block size, which is around like 1,500 chunks. That would be around like 5 milliseconds encoding, including the proof and signature. So because it's not only about the encoding, you also need to generate all those Merkle proofs and sign the root of them. So all together is like 5 milliseconds.
That'll work. And then basically what happens is they generate these chunks with some configurable amount of expectation for like loss, basically. And that is where you generate more data than you put in, basically. And that's what gives you that property. And then, based on then from there, what happens? So the leader got all these chunks. We know that they're recoverable. but they have to be recoverable on the other side of what? So they send it basically to some set of like other validators in some way, or like where do the chunks go from there?
Right. So there are different ways of designing it, right? But as you discussed, if you design it just like in a naive tree-like fashion, you are vulnerable to eclipse attacks where you just compromise the top of the tree and then the rest of the tree suffers. So the way Raptorcast works is the leader sends the chunks, some designated chunks for each validator. The leader sends them to all the validators. So if you have n nodes and you have, say, some number of chunks, you divide those number of chunks among all nodes and you send them those chunks. So the bandwidth cost for the leader is of the same order as the size of the block or the number of chunks that you have. It's just divided among all the nodes. So that's layer 1 of Raptorcast. And so what you do in layer 2 after that is, once these different nodes receive these chunks, they would perform their signature checks, verification to make sure that the data has integrity and authenticity. After that, they will then each node will send their chunks to every other node. So the second layer is an all-to-all step where if I receive a few chunks from the leader, I just send them to everybody else, so that everybody else at the end of second layer has all the chunks that the leader has sent in the first place. So this allows, if you calculate the bandwidth cost or the amount of data that's incoming and outgoing from every node, it's of the same size as the block of the same order. It doesn't scale with the number of validators. So it's perfectly dividing up the load among all the validators, so that if you have n validators and B size block, the per validator cost is only of order B rather than order scaling with order n. And so at the end, if you had sufficient redundancy in your data, I mean, we can talk about how you calculate that, what are the factors influencing it. But if you had sufficient redundancy in the data, you can be sure that at the end everybody will have enough chunks. There's some also other nice properties which are side effects of these, which is that you also have some sort of fairness among the validators, because as you might know, there are concerns around MEV and so on. Like, if you are able to get the block faster, you have more time to do computation, more time to calculate all these kind of strategic things that you want to do on top. So rather, and then you have incentive for co-location and so on. With this approach where we say, okay, everybody gets little in layer 1, and then everybody gets almost at the same time in layer 2, you also have some side effects of fairness among validators as well.
Yeah, I mean, I think, I guess like the naive way you would typically think about a tree, right, or broadcast trees, you have some smaller set you've basically sampled to be like the first hop, and then they send it to another hop. It's interesting to have like what is really like a very flat tree, very wide, which is you send little bits to everybody, and then they send little bits to everyone else, and then all of a sudden it all comes together.
So one downside of that approach could be like saying that like we're kind of like not wasting, but using the bandwidth of high stake validators for all the validators, all the nodes. So if you think about it, like for example, in Solana, 82 validators, top 82 validators can reach to the supermajority, and which is like 66% of the stake value. So, and the rest of them, which is around like 1,200 validators. So the rest of them are kind of like, I'm not saying it's waste of the bandwidth, but they can kind
You're not saying they're useless.
Yeah. But I mean, like those 80 are enough to reach the supermajority. So that's kind of like some sort of like trade-off. On the other hand, you may lose it may lead to some centralization if you only try to work around those top 80 validators. But maybe kind of like something in between could be the best solution. We can also handle that with some sort of like the kind of like prioritizing the chunks that we are sending even in the flat structure that we are, even when the intermediate node is sending like chunks to like thousands nodes, still they can prioritize that. to send the chunks first to highest stake validators. That makes the consensus much faster, as opposed to just sending them just randomly, because the first 80 can reach the supermajority, but the rest of them are still like receiving those chunks.
Yeah. Interesting. Yeah. So I mean, I guess in the architecture and environment you guys are designing for, the participants are not equal weight, right? So they do have varying weights, and so you have to factor that in, I'm assuming, into like how many chunks each participant gets, or something like that. Is that correct?
Yeah, exactly.
Yeah, I mean, this is related to Sybil resistance, right? Like, because we are working in a proof of stake setting, if we just say that all the nodes receive equal number of chunks, regardless of what their stake is, then you of course have incentives to Sybil the network, where a higher stake node would say, what am I getting by just being one node? Let me pretend to be 10 nodes. And then I control more of the network that way. So at least with proof of stake or whatever Sybil resistance mechanism you have to be kind of proportional to that, which has its both upsides, but of course downsides. And so at least in Raptor what we do is proportionally divide the number of chunks based on the stake weight. Because if we do it any other way, then we create incentives for Sybil attacks.
Yeah. So I'm assuming then, obviously, so I think, short digression here, the obvious question becomes like, how do nodes that don't participate in consensus, I guess, learn about stuff? I think this is one other byproduct of like the kind of like the simplest peer gossip approach, which is like, well, if you don't know who's a validator or not, like we kind of just send it to everybody. And like, I think there's like the Sybil problem that's inherent to that, but we won't focus on that. But it's just like, eventually, even if you're not staking, you'll kind of hear about what's going on. But in a lot of these like higher throughput, I think like proof of stake based systems, usually I would argue for good reason, the full nodes are not necessarily incorporated into this procedure. So I guess like I'm curious if it's something where you expect validators, let's say, to like offer services to people that are not validators if they want data, or is there some other mechanism you think that kind of part of this to have nodes that aren't staking learn about what's happening at some sort of latency, low latency?
Yeah, I mean that's a good point. So the way it's designed is in the default client itself, the validators would send the data to other full nodes that can register with the validators, and that they can be part of the tree. Now they may not be part of the critical tree, which is with all the validators, but there will be a separate tree where they can be a part of and receive the data, not in the critical path. But yeah, this is part of the the default / honest behavior of the validators.
Yeah. So you mentioned that there was a few things you guys tune, I guess, as you think about like the sizes and redundancy of these like codes. Maybe you want to go into a little bit of that. I mean, I'm assuming packet loss is obviously one factor. Is there more to consider, I guess, as you think about like the overhead here?
Yeah, there are like three factors that we consider to determine the redundancy. The first one is like the packet loss, as you said. It's actually two, since it depends on the number of hops. And so the more hops, we need to consider like the multiplication of the packet loss. So the second one is just the Byzantine, like the fault tolerance of the BFT protocol, which is like 2/3. So we assume like 1/3 of the nodes, 1/3 of the stake value of the nodes could be like Byzantine nodes. So on top of that, the value of this leader stake is also very important. So imagine the leader himself has like 50% of the kind of the weight, the stakes. So that now he needs to make sure with the remaining of the nodes, which probably they have like the rest 50% of the stake value, he needs to make sure that they will be able to kind of like rebroadcast the chunks to each other like properly. So the thing is, when the leader stake is high, then the influence of the Byzantine nodes in the remaining set is more sensible. So now, like, it means like the leader himself knows he is honest. So now, if, for example, in my example, if he has 50% of the stake, now in the remaining 50%, 33% are Byzantine nodes and only like 17% are honest. So it needs to make sure that in that setup, like where now the Byzantine nodes are even like more, they have more stake value than the honest nodes that are able to like kind of rebroadcast the chunks to each other properly. That's one factor. So we set the redundancy based on these three values. So, I mean, these are kind of like, these are all good for general cases, but there are some sort of like exceptions that kind of like sometimes some edge cases, some scenarios that we need to consider. One of those scenarios is the small number of chunks. So that's actually why we are saying that sometimes Raptor Codes is better than with Solomon, because for small number of chunks, Reed Solomon is good, but when it comes to higher number of chunks, Reed Solomon fails. So what I'm trying to say is that imagine just the scenario like we have like, let's say 3 chunks and 1,000 validators. How do you assign those 3 chunks to the validators to rebroadcast? So how do you select the first rebroadcaster? So you need to select 3 of them out of thousands. So there is a chance that all 3 are just Byzantine nodes, right? So unless they reach to some sort, it's very unlikely those 3 reach to very high number of stake values. So how do you select that? That's a problem that we may have. Then we need some.
Do you just like duplicate them, I guess, in that case, and just kind of like do way more than you need to, I guess, to like ensure?
Not good. We try to. That's the good thing about the rateless kind of or fountain just encoding systems. So in fountain encoding systems, it's one type of like erasure coding that you can generate as many as like codes that you want, as many as encoding symbols as you want. So because in Raptor codes, all you need to do is to just XOR new chunks to each other. But that's not the case for Reed Solomon. So you need to set a fixed kind of like number for the polynomial and design that polynomial to generate your kind of like encoding systems. That's another like dimension that kind of like led us to select like Raptor codes over Reed Solomon.
So the summary there is like basically if you're the leader and you are a high stake leader, you basically need to send things out with more redundancy basically than you would otherwise do, because the expectation is that you are honest in this scenario and that as a result, less of the people you're sending to is. Got it.
Yeah, these are all the factors which you have to keep in mind when you're designing the system and writing out your exact redundancy equations, right? Like this is my packet loss, this is the stake of the leader, and so on. This is the rounding that I want to do if I have less number of chunks. So these are the things that you want to keep in mind. But I just want to kind of like highlight that the examples that we're discussing are, of course, degenerate examples just to drive home the point that we need to take these into account. Of course, you won't have a leader with 50% stake or just 3 chunks, but
at that point, a lot's already lost. So it doesn't really matter if they're honest or not. I think so. Like, is this notion of, I don't know, like this dynamic kind of redundancy? I usually hear it more in like a static context. You're like, oh, we assume this, and this is the redundancy setting. Whereas the redundancy is kind of changing based on the leader's choice. Is that, I don't know, is that something you found commonly, or do you consider that kind of like a novel approach to this broadcast problem?
I assume this is novel. I think, like, for example, in Solana, like in Turbine, they use like the redundancy factor of 2. Like that's how they do. So, I mean, I think we need to design a system based on the assumptions. So in our system, our assumption is like 1/3 of the nodes could be Byzantine. So we need to design something to make sure that like under all circumstances, if 1/3 of the nodes are Byzantine, the delivery of those chunks are still guaranteed. So at least all nodes will be able to kind of like receive enough chunks to decode successfully. So and we want it to be kind of guaranteed with very high probability, at least based on our assumption. Maybe our assumption are wrong. Maybe over 1/3 are malicious. Maybe our assumption of packet loss is also not accurate. Maybe our assumption is 2% and the packet loss is 10%. The system fails. But at least what we want to do is to design something proportional to our assumptions, and at least addressing based on our assumptions. So, but what I'm seeing in like other solutions, that that's not like kind of the case. So I can find, at least for the previous system, like Turbine, I can find some scenarios, some edge cases, some different like weights distribution that Turbine fails, because they have just kind of like very fixed system with like 2x redundancy, and even the kind of like those nodes are selected based on weighted randomness, and that weighted randomness could be not in your favor, not in a way that you don't like that. So but in our system, I think like that's not the case. It's just like it guarantees the delivery of enough chunks to all validators in case of based on our assumptions.
So I mean, I guess maybe a specific follow-up to that is like, do the nodes, or like do you imagine whoever is using this scheme like kind of try to understand and estimate the packet loss, kind of just keep going down and down and down until something fails, and then kind of bounce back up a little bit? I don't want to call it like, it's kind of like TCP cubic style, right? Where it's like you try and see where the limits are and then back off. And BBR is a really good extension of this. But generally, I'm curious how you think about it, because I'm assuming you're going to want to like do some probing to understand what is the necessary redundancy, but then obviously that enters a whole different world of hell of like, how do you actually recover in the case that you are wrong, which eventually will happen in the wholeness of time.
Yeah, we have considered these things, and I mean, this is all part of like future iterations and so on. But what you're saying kind of makes a lot of sense, in the sense that you can see if you're having more timeouts, in the sense that the block was not reconstructed at the peers, and you kind of skipped that round and moved on to the next. Then that something wrong is going on, and probably it's because of some other reasons, or probably it's because of the redundancy. It was maybe too low for the current conditions. So you can design an adaptive system that's adaptive to both the network conditions and the adversarial threshold in your network. But that's I think in the pipeline, at least in the way we describe the blog post as of now. I'm not sure if we mentioned it in the future work, but it's definitely makes a lot of sense, promising direction.
And basically, the I always like to think about it as like any good protocol has a good backup strategy, or like ace in the hole. But basically, the way that this works is, if this fails, let's say, the consensus protocol just skip and try again later. So like obviously the voting scheme in the consensus part does not flow through this like broadcast tree, because it is, as we discussed early on, right? They're thought of similarly in the literature, but like in practice, you kind of just all to all or something kind of like it directly with the votes, which are typically very small. But this is like a different kind of construction that fits into that. Is that correct? Or are you guys thinking about?
That makes a lot of sense. When we're talking about like the system fails and so on, we are specifically talking about just the reconstruction failing in that particular slot. And if it fails, it's not a catastrophe for the larger system. You just move on to the next slot and probably be more adaptive to the conditions.
Yeah, but one potential attack is like, if like the malicious nodes are able to kind of attack the system at some point, they may attack only one validator very easily. So, and even with any like fallback mechanism, that's an issue, because the fallback mechanism is not activated just with one failure. So imagine design something which is not like Byzantine fault tolerant, with some fallback mechanism. So it works. But after seeing that, for example, the Byzantine nodes or because of the packet loss, they are just kind of messing with the network, then the fallback mechanism is activated and it goes to the Byzantine fault tolerant structure. It works good if the malicious nodes attack the system based on what we expect. But what if they not do that? What if they only target one validator when he is the leader? Then that becomes an issue. But yeah, I 100% agree with you. If one round fails, it's not a catastrophe. We can just fix that or kind of change the parameters to kind of address that. But we also need to be aware of what if the malicious nodes try to take advantage of those just one round failures.
Yeah, that's a really good call out, I think, and how you think about optimization here. I always feel like the efficient frontier is always the enemy of robustness in some kind. And I think, I don't know, when you get into this high throughput world, I think a lot of folks feel like mechanisms need to fall into this optimistic approach where it's you kind of just assume everything's going to work out, and then all of a sudden shit hits the fan and you pull into this other scheme. And as much as I've tried, at least, to avoid that, it seems like a really nice property to not, I don't know, it feels very fragile to me to be so optimistically driven just to immediately fall back with pretty little effort from an adversary. So that's a very interesting point to call out in the tuning, where you may not want to be too clever or too optimistic about if you think you're on a really good network, that you just maybe give up a little bit more redundancy than you really meant to. Yeah. Interesting.
Yeah, and I think these kind of models or these ways of building systems is also evolving as we kind of mature, as the industry matures more and more, right? We'll find out how how fragile or how what's the right trade-off between robustness and performance here. Right, do you just assume everything is optimistic? For example, in some protocols, some consensus protocols are typically designed just to have an optimistic path where there's no equivocation. And that is a much different model than the original problem that people were solving in literature, and the original problem that Bitcoin, Ethereum, and all the other blockchains started out with. And I think the jury is still out. As we kind of go through many more years of building these systems, we'll find out how much optimistic systems are going to whether there's penalty in terms of UX, whether you waste a lot of time just falling back and recovering, whether the adversaries get more mature and you have more sophisticated adversaries. Right now we don't have too many attacks happening on these systems, right? Fraud proofs, fallbacks, equivocations, we don't see too many of them. But as we kind of mature more, we may face more of these problems. And I think traditionally in literature, it's kind of divided into two models. One is a mobile adversary or an adaptive adversary, where the adversary is assumed to corrupt 1/3 nodes, but those 1/3 can rotate around the network. And that's what that's the model that Babak was concerned about. And there's one static one where you just say that the adversary is corrupt.
That's easy way out, baby. Yeah.
There are 1/3 nodes who have malice in their heart, and that's it. They don't change. And that's a much different model. Of course, one is weaker than the other. So we'll find out which models are more suitable for as we go.
So I'm curious, obviously there's a lot of interesting work here. How far along are you guys on implementing the ideas that you've described here? I think there's a Mona testnet, for example. Is that running with a lot of this stuff, or is this planned for some future work?
I don't want to kind of speak too definitively about it, because things are evolving very fast and so on. But my understanding is that Raptor is, as we describe in the blog post, and as most of what we discussed today, is already running on the public testnet. Maybe Babak, you have more info on that.
Yeah, there are some small parts. Even in the blog, we have mentioned those parts that are not in the public testnet. So one of them is the redundancy factor. So there are some small parts that has not been implemented. That I would say 95% is similar to the blog post. but some small just details are not implemented, and all of them are mentioned also, have been mentioned inside the blog post. So to make sure that everyone is aware of what's going on exactly in the public testnet right now.
And the dumb question to follow that is it behaving as you'd expect, I guess, or is it still too early to tell? I know you mentioned that we'll see what redundancy factors end up being required, but I don't know if there's any interesting learnings from like the path of actually running it, or if you guys wrote this after that.
My understanding is everything's working as intended so far. Everything's running smoothly. Yeah, I mean, any kind of timeouts or slots that were missed, my understanding is that they were not missed because of like reconstruction failing or aptcast. It was just, some validator misconfiguring, their IP address, and then you don't know where to send the packet
Classic.
to. Right. Some misconfigurations and so on. But at the system level, my understanding is everything's been running smoothly as intended.
So now I think it gets into some very interesting conversations, which is like, you've done all this work, you've come this far, right? We've seen a lot of folks now start to evaluate this idea of maybe not doing this like validator driven broadcast for that component of getting this chunk all over the place, but instead maybe using like out of protocol relays or like things that like help to disseminate data throughout the network that do not run through the validators. I even think Solana's last week talked about with Alpenglow, like this relayer layer enroader, or like kind of that fits in this world where they don't actually push the chunks always through the validators, and then instead have these maybe different types of nodes that are like multicasting everything through the network. Very different model, obviously, to think about like fault tolerance and all these different things like that. I'm curious how you think about maybe where to draw the line with optimization and where you feel like it, kind of fits into this broader story of what these blockchains are supposed to be for, right? Because if you want to go fast, right, just one node doing everything is obviously the fastest, but there seems to be some sort of trade-off between we do all this fancy coding stuff into like, well, we just put it on some big nodes that have good networks to, just running one node. So very curious to hear how you guys think about that trade-off.
I can take this loaded question first, I guess. Yeah, I think it's very interesting because the boundaries of the protocols are expanding. You can think of it that way, where the validator set is typically assumed to have this composition, this model that we have inherited from the 90s and so on, that some nodes are honest, some are malicious, but then these nodes are participating in consensus. They arrive at a total order of transactions, but the data for those transactions is communicated off band. This is like asynchronous dissemination. And then the question becomes, is that data available? What are the assumptions underneath it? And I think it's very important that when we build these systems, we are very clear about the assumptions and the the thresholds that we're willing to tolerate. And I mean, so many systems in this space are built where you assume everything is going well, and then you claim very amazing numbers that are honestly incredulous, and then you later discover as you look under the hood that there are many assumptions that are not stated, and sometimes that are not even clearly understood by even the designers of the system. So throughout the discussion, I think that props to the three of us. We have done a good job of like also highlighting the assumptions behind all of these systems. Otherwise, if you're not clear about that, then you can just assume everybody's honest, one server maintaining all the data, and everybody's just working with the hashes of the data. It's a fraught space.
Right? Well, I mean, because I think it touches a lot on, I think Babak, you mentioned like this whole notion of like, well, 80 nodes really are all it required. Like, do we really need the validators to be responsible for making sure the long tail of participants gets everything in that way? Like, some would say definitely. Others would be like, I don't know. Maybe there's something else that should be involved here to like help with that process. It's a interesting design twist to consider. I think is like, well, we've already started to rip apart these P2P dissemination strategies. What if we keep ripping them up? Like, is it better to have, if there's 30 independent relayers, like, how do the security properties of that compare to like this full, P2P broadcast? I think there's a lot of work to do to decide if that makes any sense. Tempting though, for sure.
Yeah, I think, I mean, a lot of it also points to also being clear and defining what we mean by, decentralization, security, and so on. I mean, like, we very quickly get away from, these technical ideas about data dissemination, Raptor and so on, and we very quickly go into what are we really trying to achieve by building these systems, right? Like, what does it mean for one-third nodes to be malicious, and what kind of crypto economic security we are targeting, security budget, and so on. There are many of these debates happening, and many of them get philosophical, political very quickly. But those are very, very important and good debates to have, for sure.
Yeah, another question I kind of had, kind of similarly open-ended around like kind of this broadcast kind of conversation, is we've also seen some approaches, and I think some of your previous work, Kushal, and like Mr. Seti, I think probably touched a lot of this too, is like this whole notion of like pre-consensus broadcast, where you are sending like the majority of this information long before the leader is the one actually sending out these chunks of large data, I guess, to the rest of the network. You guys have obviously chosen to rely more on like in the consensus slot broadcasting all this data out via this scheme, which should be pretty fast. I'm curious, like, over time, how you felt about this topic, because obviously you did a lot of work on this pre-consensus approach, and now this is, a different direction to take that same stuff. So I'm curious if, where you sit on that in terms of the opinion spectrum, and yeah, I guess like how you've thought about that evolve, because there are trade-offs there too. I'm not saying that either one is a silver bullet.
Yeah, I mean, definitely there are like different flavors where you either do reliable broadcast, right? Like, you make sure that the data is reliably sent to everybody else before consensus even happens.
Yeah.
And there is the approach in Mysticity where you just send the data without reliable broadcast.
Yeah.
But then, well, there are some differences there. Like, the data is still sent in the critical path, at least the implementation that I'm aware of. But then you achieve consensus on that, and then you weed out any equivocated blocks, any missing blocks, and so on. And you can also put the data in critical path and not worry about asynchronous dissemination. Various trade-offs. I think it depends. If you are okay with, if you really want to make sure that the data is being sent asynchronously but reliably, then you go with reliable broadcast, right? So that you don't have to fall back too often. But if you're just doing a best effort and then doing consensus on the uncertified data, then the inherent assumption there is that most of the time things are fine and we are not under constant attack, constant equivocation, which is a very fine assumption, right? A very fine model to operate in. And so those are the assumptions there. And of course, there's the trade-off between asynchronous dissemination and just putting the data in the critical path, which is what many chains do. And there the assumption is, I think the assumption is that the additional complexity of async dissemination is not worth the gains that you get when your size of the data is not huge. So, for example, if you consider approaches like, autobahn that you were mentioning, and, where you keep disseminating the data and then you later achieve consensus on that, the data is not in the critical path of the proposal of consensus. There, the inherent assumption when writing these papers is that you're dealing with lots and lots and lots of data.
Yep.
And you have to then eat up the entire complexity of async dissemination. But until a very reasonable limit, putting the data inside the blocks, like originally Nakamoto did, works very fine. So it depends on how much data you expect to be handling, and these are very reasonable limits. So, for example, with a few megabytes of transaction data every second, the testnet is running very smoothly, and we don't need to eat up the entire complexity of sending that data beforehand and then worrying about data availability, worrying about the complexity of synchronizing the two things at some points. we don't have to worry about any of that with very reasonable limits on the data.
Yeah, not to mention some of the fee mechanics of the pre-broadcast that get pretty gnarly in terms of understanding that you're not stuffing junk in that pre-consensus broadcast.
Yeah, I love that the questions and the nuance that you bring out are so accurate and so like hit the nail on the head, because I mean, these are precisely some of the trade-offs that these approaches are making.
All born, unfortunately, through pain, dealing with it. Yeah, I mean, I think the funny thing to me, I mean, like the thing I strongly agree with is like, if you have consensus and in consensus in the critical path, you are broadcasting the data, that to me, without all these other mechanisms, is the lowest latency way to get that data finalized. Like all these pre-consensus things, like you do this process and then you include it in consensus. Whereas like if the throughput you are targeting fits in this box of the critical path, like there is no faster way. Where like if you start to stream data out as you go, like, or you do this like really sophisticated broadcast scheme, like your time to finality from the user submission to finality, I don't know how you would go faster. And to me, that's the trade-off. I think that why these things are so interesting is basically to say, well, if you want to scale up throughput and retain that property, if you're not doing some sort of like sophisticated broadcast scheme, you will cap out because the leader just can't get the data out fast enough, which to me is a really interesting design space and why I think this is such an interesting topic, I guess, is if you get into that world, there's not a lot of options unless you employ some out of protocol relays or do some of this pre-consensus stuff, which has these other trade-offs we talked about. So very interesting.
Yeah, the way I think about it is you want to design your system with a reasonable estimate of the kind of load that you are expecting, the kind of maximum worst case demand or worst case load on the system that might be there. And then if you discover that your design is actually not compatible with that, so you're too much in the critical path, then you branch out into these very complicated systems. But until you don't need to, it's a good idea to not go there.
I think Anatoly has this interesting quote from a while ago I saw on Twitter, which is like, I pray my competitors plan for like unlimited throughput. Like you'll compromise everything to get to unlimited throughput. Yeah, funny. It's always tough when protocol design starts to become like a taste thing where you're trying to like find the right balance between these things, where it's so much easier, hopefully, if you can just rely on possibility bounds. But a lot of times, UX and the user's experience is not quite as easily described. So it's interesting.
Yeah, that's what makes it interesting, right? Like there's so many trade-offs and so many considerations that one has to do, and design systems radically different for different regimes of load on the system. It's very interesting.
Well, you guys have been extremely generous with your time here, going on about an hour and a half or so. I want to be fair and start to wrap this up. Are there anything you guys want to wrap up with, points you want to make or attention you want to call to? I know you guys are doing obviously a lot of really interesting work in this space. So feel free if I don't know if any of you guys want to say some closing words on stuff that you guys are doing or things you'd like to call people's attention to.
Yeah, just one thing from me. I mean, I personally think like all of these approaches, like different designs, they are all good and they could be good for different purposes, under different situations. They all could be better than the others. I mean, it's so hard to choose, like if to say that like the Raptor cast with Raptor Codes is the best way to go for every situation. So I would never claim something like that. Depending if the blockchain, they are dealing with a super big like blocks, maybe instead of using like the R10, it's a variation of the Raptor codes that we are using. Maybe Raptor Q is better because that's better for higher like redundant, for higher bigger data. If they are dealing with the small data, another solution is good. So here, I mean, the goal was not ever like to kind of saying that the Raptor codes and Raptor Cat is the best design. So that was one thing that I wanted to mention here.
Yeah, from my perspective, I think, some closing words. this is we have to kind of think about these. We've discussed many of these topics during this discussion, but we have to think about these things as holistically, not just designing the data dissemination layer separately from the crypto economics and separately from consensus, and separately from storage layer and so on, because many of these things crucially impact the design decisions among each other. Like for example, if your consensus protocol has mechanics to deal with like failed slots very efficiently, where you are able to recover that. For example, in Monad BFT we have some very interesting mechanisms to recover blocks and not abandon blocks like they would in typically hot stuff and the vanilla ways of implementing these protocols. Then you can actually go ahead with a different design in your networking layer, a different design in your crypto economics, right? Like for example, if you assume that equivocation is largely going to be handled by the slashing layer and handled by the crypto economics part, then your consensus protocol can build in optimistic paths where if slashing was not there, you could go much faster. So looking at these systems holistically, I think is the key to have a beautiful overall system.
Yeah, it's a still a lot to explore. I think the point you made there is funny, which is like sometimes you got to be careful, like trying to basically capture all data that comes out of these systems, because the process of doing so can be far less efficient than the actual thing you're trying to do. So like there's this very interesting balance between 10 different dimensions of the protocol design. It's like, yeah, actually, if we want to produce certified faults, like turns out someone could just spam us with faults and we'll spend all day just generating these certified faults instead of actually doing the consensus. So yeah, it's a very interesting balance to kind of walk here. But yeah, thank you both for spending the time, and really appreciate the conversation, and yeah, best of luck with getting everything all the way to production here. So thanks, guys.
Thank you for having us, Patrick. See you.